The horizons of warfare have shifted. No longer are we bound by the propeller-driven skirmishes of the last great conflict. Today, the security of the free world depends upon seizing the high ground, not merely the hills of a battlefield, but the very edge of the atmosphere itself. We are witnessing a bold leap into the supersonic age, a venture spearheaded by North American Aviation to create a machine that defies the conventional laws of drag and heat. This is the XB-70 Valkyrie. It is a weapon forged for a singular purpose: to penetrate the deepest defenses of the Soviet bloc at 3 times the speed of sound. To achieve this, engineers had to discard the aluminum skin that clad our Mustangs and Sabres. At Mach 3, air friction generates temperatures that would melt a standard airframe. Thus, this Leviathan is constructed from a honeycomb of brazed stainless steel, a material so stubborn to work with that entirely new welding techniques had to be invented on the factory floor. Observe the geometry of the wings. They are not static. In flight, the outer sections fold downward, not for storage, but for stability. By drooping these wingtips, the aircraft captures the supersonic shockwave generated by its own nose, riding atop it like a surfer on a wave. This phenomenon, known as compression lift, allows this 200-ton giant to cruise at 70,000 feet with terrifying efficiency. Even the landing gear is a marvel of necessity. The tires are impregnated with aluminum powder, giving them a distinct silver hue. This is not for decoration, but to prevent the rubber from decomposing under the infernal heat generated by friction. Furthermore, the fuel itself plays a dual role. Before it is consumed, it circulates through the airframe to absorb the massive thermal buildup from the avionics, acting as a liquid coolant. It is a closed loop of survival, where the very lifeblood of the aircraft prevents it from melting from within. Beneath the fuselage, 6 massive General Electric turbojets, aligned side by side, drink fuel at a rate that staggers the imagination. They provide the thrust necessary to outrun any interceptor in existence. Yet, the peril lies not only in enemy fire, but in the physics of flight itself. The pilots are encased in individual ejection capsules capable of snapping shut like a clamshell to preserve life should the pressurized environment fail. We are looking at the pinnacle of strategic power, a white arrow aimed at the heart of any aggressor who dares to challenge the peace.
More than 1/4 century after its maiden flight, the XB-70 stands as one of aviation's greatest achievements. This is the XB-70 Valkyrie, a supersonic heavy bomber that featured design innovations decades ahead of the planes of its time. Yet, this revolutionary aircraft never went into service, because while it was being developed, the strategic picture changed. Designed as a replacement for the Boeing B-52, the XB-70 could travel at 3 times the speed of sound, employing technology that was well ahead of its time. The XB-70 is one of the best aircraft designs that never went into production. A decade later, a similar fate almost befell this plane, the B-1 bomber. Apart from modifications to the engine intake, the B-1B seen here looks very similar to its controversial predecessor, the B-1A heavy bomber. However, because of the evolution of technology, the B-1B in many ways was a very different aircraft.
Previous reports have described the progress of the XB-70A from the early stages of planning to research and development, and finally, through fabrication. Now, during this report period, a major objective of all previous effort has been achieved through the completion of the first phase of flight testing of ship number 1. Looking back to early July, the testing of its various electrical and hydraulic systems had just been completed, and the XB-70A was moved out of the hangar to the engine run-up area for its final pre-flight checkouts. First on the agenda was fuel system calibration. cockpit fuel quantity gauges were checked, as known amounts of fuel were pumped into each tank. At this time, the airplane's fuel transfer and fuel distribution systems were also checked out. Installation of the flight test instrumentation package was completed. In flight, its 3 tape recorders gather information on the pilot's control positions, control surface movements, and temperatures and hydraulic pressures throughout the airplane. And for the first time, the engines were operated in the airplane. Through single and multiple engine runs, pre-flight crews checked engine performance, thrust control systems, instrumentation, and secondary power systems. The flight controls, previously checked out in the hangar, now perform perfectly on air vehicle hydraulic power. All efforts were then directed toward preparing the plane for taxi tests. The first taxi run was started on 9 August. At the controls were the men who would take command on the initial flights. The pilot, Al White, chief test pilot for North American Aviation, and the co-pilot, Colonel Joe Cotton of the United States Air Force. Some problems were encountered in the hydraulic system and required minor modifications of hydraulic pumps and associated plumbing. The fourth in the series of taxi tests, conducted on 25 August, was a complete success. An initial run was made to 87 knots to check nose wheel steering, brakes, and ground handling characteristics. The high-speed run. It reached a speed of 122 knots. Further checks were made on nose wheel steering and ground handling. The drag chutes were deployed at 122 knots, and moderate braking was applied. Chutes were jettisoned at 80 knots. The plane was stopped with ease through moderate braking. 2 more taxi runs were made, followed by countless checks and rechecks of the various systems and instruments. The XB-70A was ready for the big day, September 21st, 1964. White and Cotton were at the controls. Their mission? Take off from Palmdale, follow a scheduled flight plan, and land at Edwards Air Force Base.
5, 4, 3, 2, brake release now.
At 8:38 in the morning, the wheels started rolling. Acceleration was rapid and liftoff occurred under 5,000 feet. With all engines at military power, the climb continued steadily while all systems were checked and controls tried out. With all systems in the green, the gear handle was moved to the up position. The main landing gear has a 3-stage retraction cycle. First the bogies fold, then the struts rotate, finally retract aft. The gear started into the rotation cycle, then it stopped.
Who has rotated and stopped is not folding. Okay, they are static, is that right? They're not moving? That's correct.
The gear handle was placed down. The landing gear returned to its normal extended position and locked in place. The flight proceeded in accordance with an alternate plan to gather low-speed handling and stability information. Because of an indication of overspeed, one engine was shut down. The flight continued unhampered. After an hour of flight in the vicinity of Edwards Air Force Base, a low-altitude pass was made over the runway, then the final approach.
We're going to land out of this one. Okay. Chase, if you obviously see me leveling off a little high, well, let me know. Huh? Affirm. I'll give you a countdown from about 50 feet. Okay. 50 feet. 30. 20. Full. Flat. And you're on. Beauty.
gear.
Drop gears on 5.
The pilots landed unaware that a brake was locked. The 2 rear tires blew out and started burning. But there was no difficulty in controlling direction, and the plane was brought to a perfect straight line stop.
Very good, Jettison. Jettison.
Jettison. Jettison Mach 74.
Looks as though your aft tires are blowing and they're both burning, but not very badly. You've got 3 fire trucks with you.
Fire crews closed in and extinguished the blaze in the wheel area. While the first flight did not proceed exactly to plan, it did prove the takeoff and landing characteristics and showed low-speed handling qualities to be quite favorable. Total flight time was 1 hour and 7 minutes. The brake problem was solved, a faulty switch in the landing gear system was replaced, and the engine overspeed condition was corrected. On the 5th of October, the plane was ready for its second flight. The plan was to collect data at subsonic speeds, then move gradually up toward a speed of Mach 1. After the main landing gear refused to retract on the first flight, attention was concentrated on the underside, the landing gear area.
Here we go with the gear on the count. 3, 2, 1, gear up.
Handle up. Doors are opening. 3 green lights are out. Looks good. Nose gear is up and door locked. We're in the wheel well. And both main gear doors are coming closed, and they're closed, but it looks clean now.
They came up in a perfect retraction cycle, and the doors closed. Gear retraction completed successfully. White and Cotton took the plane up to 16,000 feet for the first series of tests. Wing flutter and stability checks were made between Mach 0.52 and 0.68. Flight remained in the Edwards Air Force Base area. Another climb was set for 35,000 feet. During this climb, at an altitude of 28,000 feet, a caution light indicated a pressure loss in one of the 2 utility hydraulic systems. As a precautionary measure, the landing gear was lowered, and following standard safety procedures, the decision was made to land on the 11-mile-long runway of Rogers Dry Lake. Touchdown was smooth, rollout perfect, and the brakes operated normally. From a post-flight check, it was learned that a broken hydraulic line had caused the pressure loss. The pilots reported that the plane handled well and as predicted, and that extensive stability and flutter data was obtained. Just 1 week later, flight number 3. Takeoff and climb out were normal, and landing gear retraction was perfect. More handling and flutter checks were made, and with the confidence of past experience, speed was pushed up to 0.95. The afterburners were lit, and the XB-70A pushed past the speed of sound to Mach 1.1. 3 times the plane made the jump from subsonic to supersonic speeds. For a total of 20 minutes, the research plane was above the speed of sound, testing, checking, gathering data. On the letdown to Edwards, it became obvious that the plane had lost some of its paint. It was too thick, it became brittle, and when the structure flexed, some paint broke and peeled off. Pilot comments were enthusiastic. Handling qualities at high subsonic speeds and above Mach 1 are the same. There is no trim change. The systems, engines, telemetering, communications, all performed normally. On the 24th of October, the 4th takeoff was made. As planned, the plane climbed directly to 30,000 feet, and the wingtips were lowered. The folding tips are a vital part of the aerodynamic design. They add stability and reduce drag in supersonic flight. With the tips down at the 25-degree position, full afterburner was selected. From Mach 0.95, the plane moved through the transonic zone and up in Mach number. The test goal of Mach 1.4 was reached, almost halfway to the design goal of 3 times the speed of sound. The XB-70A headed back to Palmdale. Its Phase 1 flight test program had been completed. In just 1 month, over 5 hours of flight testing was logged, with 55 minutes at supersonic speeds. Now it's going into Phase 2 test, a complete proof loading of all control surfaces. When these checks are complete, the research plane will push on up to its design goal, steady cruise at Mach 3 at an altitude of 70,000 feet. In addition to the obvious success of ship number 1, extensive progress has also been made on ship 2 during this report period. Mating of the fuselage was completed, and final installations have started on hydraulic lines and air vehicle and instrumentation wiring. Also within this 6-month period, all fuel tanks except number 5 have been sealed. This represents 91% of the total fuel capacity. Sealing of tank 5 is nearly finished. The use of cove sealing strips along bulkheads and in corners has greatly reduced the time required to seal ship 2 tanks. Crew compartment wiring is also complete. The pilot and co-pilot instrument and console panels have been pre-fit, and pressurization checks of the crew compartment are underway. On the 4th of August, the night crew moved the left wing into the final assembly area. As with ship 1, wing tank sealing was accomplished with no difficulty. It is these rakish delta wings, combined with the long nose section, that help give the XB-70A its part spaceship, part airplane appearance. On the 2nd of October, the horizontal stabilizers, the canards, were installed. These surfaces keep the airplane balanced in flight. They also incorporate flaps, which allow decreased takeoff and landing speeds. Takeoff speeds and distances are comparable to those of current commercial jet transports. In mid-October, the vertical stabilizers were fitted in place. Unlike conventional rudders, These operate on a canted hinge line and at supersonic speeds allow much greater directional control with small movements. By the end of this report period, the last major assembly operation, Wingmate, was well underway. A modification was made on Ship 2 to provide improved aerodynamic stability. It was accomplished by adding 5 degrees dihedral to the wings and incorporates a new method of wing attachment. The wing is moved outboard 3 inches and rotated upward 5 degrees, providing the dihedral. Transition sections bridge the gap. They are made from honeycomb panels similar to the wing and wing stub. Each panel covers one structural bay. Between each set of panels is a shear web. Both top and bottom panels are fusion welded in place by a specially developed telescoping welder. The undersurface is observed through a periscope. Through this technique, Wingmate is facilitated. It actually takes place section by section. When assembly crews finish this operation, ship number 2 will be structurally complete. On the 23rd of December, the left wingtip was installed on the airplane. The XB-70A folding wingtips are the largest flight surfaces that have ever been moved during flight, each one over 500 square feet in area. Rollout is scheduled for late spring of 1965, with first flight in mid-July. Through flight testing of the 2 XB-70A research airplanes, studies will be made at Mach 3 and at altitudes of 70,000 feet. The experience of sustained flight at these speeds and altitudes will help pave the way toward safe and economical travel in the supersonic transport and the military aircraft of tomorrow.
I was told that I had been made a brigadier general. I learned later that General LeMay was in a meeting with Secretary McNamara. At one point in time, General LeMay was director of research at the Pentagon level, at the Air Force level, and under him he had a lieutenant colonel by the name of Robert McNamara. So this was a subservient individual to 4-star General LeMay. Well, now the roles are reversed all of a sudden, and that's when McNamara asked LeMay, how many general officers do you have running these billion-dollar programs? And the B-70 at the time was a $1.4 billion aircraft program. So I got noticed immediately that I was now running the XB-70. And it was kind of startling because all of a sudden I had to shift gears from being a director of laboratories to a program director, which is entirely different. The B-70 program at the time had been programmed to develop 3 aircraft. The number 3 aircraft would be the bombing navigation version. The first aircraft was pretty well handmade. The second airplane was made much better. And of course, the third airplane would have been perfect with the bomb nav system in it. But it was canceled when it was about 75% completed. In fact, I like to tell the story that characteristically in the Air Force, the bombing navigation system is traditionally late, 1 or 2 years late. The airplane is sitting on the ramp ready for that to be put in, and it's waiting for the delivery. In the case of the B-70, believe it or not, the bombing navigation system was on the dock, ready to be installed, and the airplane it was to be installed in was canceled. The wingtips rotated downward at Mach 3, or any supersonic speed, because it contained that contained the airflow underneath the aircraft instead of dissipating it out to either side. So the airplane was riding on the same thing a canoe does when it's powered. You know, it's up there on a crest, and that's the compression lift aspect of it. The engineers that designed it at North American figured that was what would happen, and they confirmed it in wind tunnel tests. So it's nothing more than containing the airflow underneath at supersonic speeds. The airplane itself was a monster, really, a huge airplane, and it was capable of flying to Mach 3. At that same meeting, when we broke up, General LeMay pulled me to one side and said, "Do you think it's ever going to go to Mach 3? And I said, "Yes, sir, it will. It's going to hit Mach 3. In fact, it went to Mach 3.2. And so actually it fulfilled what the intention was. And I watched the program and progress of the B-70. It was coming along fine. The big problem was fuel leaks. When you consider how huge the fuel tanks were and trying to get them to seal properly from leaking fuel, it was just an impossible program. I happen to know, because I was cleared for the information that was being accumulated by the SR-71, that they had solved their fuel leak problem. And I found out that they had a certain contractor who could do it. Then I passed this information on to the North American people. They were very suspicious of where I got the information and how, and I wasn't able to tell them. But I was able to tell them, go to this contractor and he will solve your problem. Well, it was a 1-year delay in production of that aircraft, believe it or not, because of fuel leaks. We'd put a certain type of material down on in the in wings, and then some clown without canvas boots would walk across it and tear it up. Now you got to go through all the curing, applying, and so forth. That's what delayed the airplane considerably. Our big problem was keeping the surface of the airplane properly established. We had trouble with tires. The tires would come up into the wheel well, and they were eventually exposed to about 300 degrees Fahrenheit and would burst, and so they'd have a problem landing with them. So Goodyear had to design different types of tires for the B-70, including interwoven aluminum threads to keep them from rupturing. So it was a nightmare temperature-wise. I wanted to be on the first flight when it flew, and it would be flying out of Palmdale and then land at Edwards Air Force Base, where it would continue its flight test. The chief engineer, Mr. Swanson, said, "Okay, we can rig up a seat belt, a safety belt, on the water tank that's directly behind the two pilots, and we'll equip you with a parachute in case you have to bail out, because the two pilots will be going out in capsules." So he said, "I want to show you one thing, however, before we make that decision." And he took me up into the cockpit, and he asked me in a little door to look back, and I'm looking back at an intake with 3 engines embedded in it, and he said, when you go out, where do you think you're going to go? And I said, well, never mind being on the first flight, forget it. Because that huge, like a big house, would have sucked me in. Obviously, I wouldn't have ever been able to survive the crash. The first flight, all the tires blew out. There were streams of flame from going behind the airplane. All of them blew out because the sensing device locked up all the wheels instead of taking the pressure from the cockpit and braking them gradually, as you now have on automobiles and so forth. They locked the minute they applied pressure, brake pressure to the both sides. The wheels locked, the sensing device malfunctioned, they locked, and they blew them all out. I was on the midpoint where they landed at Edwards. I rushed over before they got. They flew about 30 minutes or so in the air and just tested out general characteristics of the airplane. And I saw that airplane land, a beautiful landing, and all those tires blew out. Well, the XB-70 was a favorite punching bag by Secretary McNamara. For some reason, he was convinced we didn't need the B-70 because of ballistic missiles. They would gradually replace any bomber effort. Secretary of Defense decided he didn't want to put the XB-70 into production. Then he suggested we continue the program until expiration of the funds to contribute technology to a so-called national supersonic transport program. So we did continue with the two aircraft, and of course the second aircraft was involved in a mid-air collision, and this was when I was in Japan with 5th Air Force. And it was just one of those tragedies that never should have occurred. And a lot of people were disciplined as a result. A GS-15 civilian, which is as senior as they get at the time, was reprimanded because he permitted a so-called photo flight to be authorized with 5 aircraft involved, the B-70 leading it, all equipped with General Electric engines. And so General Electric wanted to capitalize on this, and unfortunately the NACA pilot, NASA now, in a 104 got in too close to the overflow of the huge wing in the B-70 and was pitched up. His aircraft was long enough to take the tips off of the top of both rudders on the B-70. And I had chased the B-70 on a flight in a B-58, which has a lot more inertia. And I got in very close to the wing. When you're flying formation, you normally try to pick a point that you concentrate on to judge your relative motion. It was huge looking at the B-70 wing, and it was tough really to concentrate on any particular point. So I felt being sucked in to the flow over that wing, but the B-58 was large enough on its own that I got out of it. And I think that's what happened to the 104. It didn't have enough inertia and so forth to get back out once it got sucked in and it pitched.
Probably the biggest single step forward in the search for new technology to gain higher speed came with the advent of the jet engine. Although pre-war Germany first utilized jet power, American engineers also tested the concept on experimental aircraft before the war's end, with aircraft like Bell's Aerocomet. The first major development of the post-war year was the record-breaking Bell X-1 rocket-powered experimental aircraft. Dropped from a Second World War bomber on December 9, 1946, in the hands of test pilot Chuck Yeager, the X-1 broke the sound barrier for the first time. Further development produced the X-2, which flew faster and higher than its predecessor. The quest for higher speed put phenomenal stress not only on the aircraft, but also on their pilots. The risk of even a minor malfunction at the speeds now being attempted was enormous. Much of the data gathered by the X-airplane tests was used for military objectives. Faster aircraft would be harder targets to hit. Some of the lessons learned from the X-airplane program were applied to American fighters and bombers. With the Cold War on, stretching the boundaries of speed and distance had become a matter of national security. By the mid-50s, the Strategic Air Command, known as SAC, was deploying its first all-jet long-range heavy bomber, Boeing's B-52 Stratofortress, a giant plane with 8 jet engines suspended below fully swept wings. The B-52 could fly at speeds of 600 miles an hour with a large payload. But although the B-52 was one of the major successes of post-war aviation, it was not supersonic. The next step in the quest to increase the speed of bomber aircraft came with the B-58 Hustler. This delta wing was developed by Convair to produce a bomber aircraft which could actually fly and sustain at supersonic speeds. But to attain this performance, the plane had to be relatively small and could only be classified as a medium bomber. During the early 1950s, when Soviet America tensions ran high, SAC wanted a bomber at least as large as the B-52, but faster than the Hustler. This was a very tall order for engineers to meet. Taking a heavy bomber past the sound barrier required a phenomenal power source. Temporarily discarding normal jet power as inadequate, aviation companies looked towards two alternatives. The first was nuclear power, used to successfully propel submarines. Convair converted a conventional B-36, not unlike this one, to carry aloft a fully commissioned nuclear reactor. The crewmen were insulated by lead shielding, and although no attempt at this stage was made to transfer power to propel the aircraft, tests were carried out in earnest. Various designs were put forward for bombers which would at least in part be nuclear-powered. However, the biggest problem here was the ramifications of a nuclear-powered plane crashing in a populated area. Another proposal to boost power would be equipping bombers with external tanks of fast-burning zip fuels, such as boron. Prior to the plane making its final dash to its target, the enormous fuel tanks would be dropped, lightening the aircraft for attack. But an ingenious solution to the problem came forth from North American Aviation. The company had refined the concept of compression lift. Their plan called for mounting 6 enormous jet engines in a tapered shape under the aircraft, thus forcing air away from the center section at high speed. The design also allowed for this air to be trapped by the outer edge of the wing when it was lowered. The compressed air would act to lift the aircraft and help propel it 3 times the speed of sound. The design was given the name XB-70, and SAC approved it for development in December 1957. North American had a long string of successes, including the development of the twin-engine supersonic Vigilante bomber for the US Navy. This aircraft combines speed and bombing capacity never previously available to carry it. But now, having put forward the compression lift concept for a high-speed bomber, North American's big problem was heat. Wind tunnel tests proved the theory could work, but the great speeds the plane would fly at would produce such heat that all conventional materials would warp. To tackle the problem, North American employed a honeycomb sandwich material made from stainless steel. This offered strength and dissipated heat. After 12 months of testing designs and mock-ups, an order was placed for one XB-70. But the aircraft, now called the Valkyrie, was in for a stormy time. But at least the concept was still alive, and its proponents hoped it still might ultimately be accepted for military use. By 1963, at least one aircraft was well underway. The first XB-70, serial number 20001, must have been an awe-inspiring sight for those lucky enough to see it. But it was not until May 11th, 1964, when the press and public were given their chance to marvel over North American's sleek white wonder. Brigadier General Fred J. Ascani, who directed the B-70 System Program Office, described the plane's various features.
Most of the structure in the wings and fuselage is of stainless steel. These are our now famous honeycomb core sandwich panels, and many of the outer skins on these honeycomb panels are as thin as 7/1000ths of an inch. The 2-man crew will sit side by side. The crew station in this position is about 20 feet above the ground. All of the space aft of the crew compartment is taken up by fuel, both in the fuselage and in the wing.
Before the XB-70 was poised at the downwind end of Palmdale's 12,000-foot runway for its first flight, numerous ground tests would have to be performed. Shortly after its debut to the public, the aircraft was again up on jacks, while its electrical and hydraulic support systems were thoroughly tested. All moving surfaces were subject to vigorous testing. All flight controls, including the forward canards, the elevons and rudders, were fail-tested and tested again. Like so much of the XB-70, the landing gear, which had to support the plane's phenomenal weight as well as the added stress of landing and takeoff, was for the time a unique and brilliantly designed feature. The forward twin wheels were conventional, but the support gear was required to rotate as well as fold the four-wheel bogie mechanism, which was stored in the limited space available. The whole process of extending and retracting the clever but complex gear could be achieved in little over 20 seconds. All of the many complex tests that took place during the weeks before the first takeoff were recorded in a special flight test instrumentation package. A self-contained airborne unit. This device was the first of its kind. It was carried in the aircraft's bond bay, and remained with the plane for ground taxiing and flight tests. The XB-70 prototype was also subjected to vibration tests that were designed to expose the gigantic fuselage and wing surfaces to the effects of vibration far beyond the point it might encounter in flight. As the aircraft test proceeded, aircrews were introduced to some of the engine's characteristics. Here at the Arnold Engineering Development Center in Tennessee, AYJ-93 engine was set up in a simulation of the Valkyrie. The engine was installed in a test chamber to give the flight crew their first experience with its enormous power. The conditions were artificial but similar to what the crew would experience in flight. Seen here is Al White, North American's chief test pilot, the man chosen to command the XB-70's maiden flight. With him is Air Force Colonel Joe Cotton, the co-pilot for much of the early test program. The backup crew shown here are Van Shepard from North American and Lieutenant Colonel Fitzhugh Fulton. For months, these men were embroiled in the business of learning how to fly the world's most advanced and ambitious aviation project. By early September, most of the exhausting static tests had been completed. Now, the most revealing tests would begin. Tests with the aircraft in motion, then, eventually, tests of the XB-70 in flight. Before the engines were fired up, the complicated in-flight recording systems were primed to record every technical event as it occurred. This view of the Valkyrie gives a clear picture of what was to become known as the six-pack tightly grouped together. This phenomenal powerful combination of 6 jet engines were to propel the Valkyrie to speeds considered impossible only a few years before. Now, hundreds of mechanical functions were checked. They would have to perform perfectly if the Valkyrie project was to succeed. The aircraft was removed from all external power sources. After a series of taxi runs, pilots and technicians were satisfied that the Valkyrie was ready for its maiden flight. On September 21, 1964, The XB-70A positioned itself at the end of the Palmdale runway for a historic moment with North American Aviation and the United States Air Force. Here, as planned, White and Cotton were in the cockpit. At exactly 8:38, the Valkyrie took to the air for the first time to begin a series of epic-making test flights. Accompanied by a single chase plane, simple routine checks were made as the pilots experienced the ways of the Valkyrie in flight. One of the first tasks was to retract the aircraft's advanced landing gear, but the mechanism failed to respond. With hundreds of millions of dollars of high technology in his hands, White set the landing gear back into its original position. The gear slowly responded to the cockpit control. Clearly, the first tests were to be made wheels down. Nevertheless, an alternative plan was available, and the plane continued on its maiden flight, although one engine was shut down when a warning light flashed. Over 60 minutes of valuable testing was gained by the time the aircraft headed back home to Edwards Air Force Base.
50 feet. 30. 20. 5. Hang on. A beauty.
On landing, one of the rear brakes locked, setting that landing gear on fire. Sitting 20 feet above the ground, with the aircraft handling impeccably, the crew had to be told to the fire by the chase plane. Two weeks after its first flight, with its landing gear, engine, and brake problems all resolved, the XB was ready for its second trial. On an early autumn morning, pilot Al White rotated Test Air Vehicle No. 1 into flight. This time, there were two chase planes so the landing gear retraction could be viewed from both sides. A second attempt was made to lift the gear in flight. Again, anxious moments passed as the chase plane's crews watched. Now, with the landing gear stowed away, the Valkyrie could begin tests at higher speeds. As the plane climbed to altitude, a warning light flashed in the cockpit, alerting the pilots to a minor failure in one of the hydraulic systems. As a precaution, White lowered the landing gear again and pointed the aircraft towards an alternative destination, Rogers Dry Lake, which proved the security of an 11-mile natural runway. The approach was smooth, the brakes operated effectively, and the Valkyrie made a perfect landing. After the flight, it was learned that a fractured pipe had set off the warning light. But considering the enormous complexity of the aircraft, this and the other problems encountered were hardly unexpected. The pilots reported that the Valkyrie behaved in a predictable and comfortable manner. They were coming to terms with the world's most powerful aircraft. While the first prototype was being tested, construction of the second XB-70 proceeded steadily. The massive tubular fuselage was married to the six-pack. The enormous white fins that would direct the Valkyrie were already in place. Lessons learned from the construction for the first prototype rapidly reduced the manufacturing time of Air Vehicle Number 2. The second aircraft differed from the first in a subtle design change. An extra 5-degree dihedral was added to the wings to improve flight stability. Here, one of the massive wingtips is being fitted. This unique feature was, until recently, the largest single moving surface unit fitted to an aircraft. The presence of these wingtips would enable the unique compression lift principles to propel North American's brainchild into the transonic stage. Back at Edwards, Air Vehicle Number 1 was rising into the sky again. Now, White Cotton and the engineers had sufficient confidence to push the Valkyrie beyond the speed of sound. On no less than 3 occasions, the plane was taken supersonic, then lowered to subsonic flight. But doing this stressed the aircraft, which was designed to be flexible. As a result, much of the thick white paint that covered the aircraft's surface flaked and peeled away. But all concerned would have agreed that it was a small price to pay to get the XB-70 past the speed of sound. However, for this aircraft to reach Mach 3, it would have to go much faster, and testing continued. October 24th saw the plane's fourth takeoff at approximately 40,000 feet. The folding tips, which had previously never been used, were lowered to the halfway position. This would improve the aircraft's stability and reduce the wing drag effect. At this stage, Cotton applied full afterburners to the six-pack, and the slender right shape of the Valkyrie began its steady increase in speed. On October 14, 1965, during its 25th flight, at an altitude of 70,000 feet, wingtips fully lowered, Air Vehicle No. 1 reached its goal, 3 times the speed of sound. But despite its technical success, and its success at meeting SAC's need for a heavy bomber many times faster than the B-58 Hustler, the Valkyrie was not destined to be adopted in military service. The Air Force, knowing the plane would not be accepted as a bomber, had tried to acquire 150 Valkyries for a reconnaissance role. But the survivability of high-flying planes over enemy airspace was now considered doubtful. Soviet anti-aircraft missiles had managed to down a U-2 spy plane which could fly at heights previously considered safe from any attack. Missiles also competed with high-speed bomber concepts within the US Air Force. The SAC now had intercontinental ballistic missiles to carry their nuclear bombs, weapons that were more economical and unstoppable than airplanes. From the early 1960s on, the ICBM was considered the primary means of delivering nuclear weapons. The ICBM also allows the Navy to play a role in strategic bombing, as its submarines offered platforms that were highly mobile and could not be detected. Like the XB-70, the B-1A was designed to replace the B-52 as the Strategic Air Command's high-altitude heavy bomber. However, due to political conflicts and technical problems, the project was cancelled. But the B-1 didn't die. Over the next several years, the US Air Force and Rockwell, the plane's manufacturer, revised the aircraft parameters. Taking full advantage of the aircraft's swing wing potential, Rockwell redesigned the plane for long-range, low-level missions. The plane was outfitted with the latest detection evasion electronics. But the major difference between the B-1A and the B-1B is that simply the later model, although the product of considerable technical innovation and years of additional development, was actually made to be slower than its predecessor. Radar jamming and stealth technology have changed the specifications for strategic bombing aircraft. But this is a relatively new development. For much of the century, the military constantly sought faster and faster planes. The XB-70 faced an uncertain future. Despite the Pentagon's decision not to deploy its supersonic bomber, Air Force testing of the 2 XB-70 prototypes continued. One unique feature of the plane, the crew escape capsule, was a masterpiece of engineering. Should the Valkyrie depressurize, the capsule's clam-like top and bottom shells would automatically roll forward and completely engulf the crew member in an airtight module. From there, the pilot would still have limited control over the aircraft, and, if necessary, the entire capsule could be fired from the plane into the air. These capsules were to play a very important part in the final chapter of the Air Vehicle No. 2. Seen here, with its slightly raised wings, the Air Vehicle No. 2 takes off on a routine test mission on June 8, 1966. Al White was in command, but he had a new co-pilot, Major Carl S. Cross, beside him. Cross was an extremely experienced pilot who had just joined the XB-70 project. At 8:27 in the morning after testing, the Valkyrie joined the formation with 4 chase planes. The event would be recorded by an accompanying Learjet. The exercise was simple enough and shouldn't have presented any problems. On the Valkyrie's inside right was an F-104, flown by test pilot Joe Walker. Walker, who was slated to join the XB-70 program, probably had more supersonic experience than any man alive. He recently completed a flight program on North American's X-15, the fastest plane on Earth. Flying below and slightly behind the Valkyrie's right wing, Walker's F-104 starfighter somehow veered too close to the Valkyrie. This shot, taken from the aircraft on the Valkyrie's left, is reversed to give some indication of what Joe Walker may have seen moments before his starfighter collided with the XB-70's wingtip. Possibly the vector effect on the giant bomber pulled the little fighter into its massive wingtip. In any event, in the matter of seconds, the F-104 was hit and rolled into an inverted position across the top half of the Valkyrie's massive frame. As it did so, it struck both the XB-70's vertical fins and the left wingtip. Therefore, it fell thousands of feet to its destruction. Then, with a dreadful shudder, the Valkyrie rolled over and started on a steep spin. Al White reached for the ejection mechanism within his capsule and fired out of the stricken aircraft seconds before it struck the desert. His co-pilot was not so lucky and remained in the plane. Probably the G-forces of the descent stopped his ejection. By 9:36, Air Vehicle No. 2 was reduced to a smoldering carcass in the desert. Emergency helicopters rushed to the site, but there was little chance that Major Cross could have survived. However, about 10 miles away, the escape capsule containing Al White was spotted. Al was badly injured, and over the next several days, his life hung in the balance. His capsule had not landed correctly, but mercifully, his pilot seat had broken when it reached the ground, reducing the impact. Over the days that followed, technicians and project officials studied the records for clues, but the story was simple enough. Somehow, the little F-104 fighter had accidentally collided with the XB-70. And on that fateful morning, in one action, America lost 2 brave test pilots and one of the only 2 Valkyries ever to be produced. Al White, the Valkyrie's first pilot, and the man who flew more flights on the XB-70 than anyone else, recovered from the crash, but never flew the XB-70 again. After Air Vehicle Number 2 crashed, the remaining XB-70 continued to be tested over a period of 5 years. It was to log 83 test flights, and the research that it, and it alone, could do would provide valuable information for supersonic transport evaluation and many other projects relating to size, weight, heat, and speed. But in some ways, the Valkyrie had also been a military success. Years later, it was learned that the Soviet Union so feared the potential of the XB-70, but it had tried to develop its own smaller version. The Soviets' fear of the Valkyrie was also demonstrated in another way. For it's now known that the Russians developed at a tremendous expense the high-performance MiG-25 Foxbat. This fighter's sole function was to protect Russia from high-flying supersonic bomber aircraft. Aircraft like the Valkyrie. The paradox was that it seems likely that Russian scientists used North American vigilante bombers as patterns for the Foxbat. The similarities are just so close, both in size and in shape, that it seems certain that the Soviet designers used American research of the early 1950s to protect the Soviet Union from American bombers of the 1960s. Eventually, the one remaining Valkyrie was phased out of test service. Air Vehicle Number 1 landed for the last time at Wright-Patterson Air Force Base, home of the United States Air Force Museum. Piloted by Fitzhugh Fulton and Ted Stumfall, it was still collecting valuable data even on its last flight. Shortly before it was signed over to the museum curator, complete with its logbook and a brief ceremony, one of the pilots is reported to have said, "I would give anything to keep the Valkyrie in the air, except pay for it myself." The Valkyrie program has become expensive. The cost of the project, divided by the number of flights, costs American taxpayers $11 million every time it took to the air. But there can be little doubt that North American aviation engineers had not only achieved a technical wonder, they had produced one of the world's truly magnificent and unique planes.
This is the North American Aviation B-70, a manned weapon system for the Strategic Air Command. Its range, intercontinental. Speed, Mach 3 all the way. Altitude, in the order of 80,000 feet. Its basic mission is the destruction of enemy targets through high-speed, high-altitude penetration and manned bombardment. B-70 squadrons are being designed to be compatible with the SAC alert concept. On alert status, the B-70 will be fully fueled and combat loaded, parked in the cocked condition for 7 to 10-day periods. The scramble signal is given. The design objective is that within 3 minutes, individual B-70s must be taking off. And within 15 minutes, at least 1/3 of the unit's strength must be on its way. In approximately 3 hours, a target 5,000 nautical miles away can be destroyed, and the bomber returning. Throughout its mission, the bomber has the ability of recall or change of mission and can also attack several targets during each penetration. Requirements for rapid dispersal of air vehicles and simultaneous starting of the 6 engines due to the alert concept led to development of a mobile flyable alert pod. It can be carried to dispersal areas by the B-70 at subsonic speeds and provides a single integrated ground power supply. It can be quickly released after engine start. Powered by 6 GE J93 engines, the B-70 can perform its basic mission on JP6 fuel only. The airplane is designed to carry high-energy fuel for consumption in the afterburner only for further range increase. The 6 engines develop a total of approximately 155,000 pounds takeoff thrust. The B-70s will have the capability of operating from existing SAC bases using today's runways, which average 11,000 to 13,000 feet. Design takeoff ground roll will be approximately 7,500 feet. The selected configuration for the air vehicle provides the maximum lift-to-drag ratio for cruising at Mach 3. The basic aerodynamic shape is a delta planform with a canard surface. The low wing loading combined with the canard make possible a reasonably short takeoff distance and low landing speed. A thin, low aspect ratio wing is located aft for most efficient lift and control. In the wing region, the shape of the fuselage provides very favorable supersonic pressure fields. The underbody of the aircraft creates a compression field behind the shockwave. A major aerodynamic advantage is gained by designing the wing to fit over this pressure field, thus providing substantially increased pressures under the wing, and consequently allowing flight at reduced angle of attack. The resulting decrease in drag contributes substantially to the range of the B-70. Elevons are provided for pitch and roll control. Directional stability is by dual vertical fins with trailing edge rudders for directional control. Wingtips are rotated downward to provide added directional stability during supersonic flight. The tips are returned to the horizontal for additional lift at low speeds. Much of the skin of the B-70 will consist of stainless steel sandwich panels to provide strength and insulation at elevated temperatures. Equilibrium temperature is expected to be about 600 degrees Fahrenheit. The crew compartment is an island of safety, with all structures, including the windows, designed for extra strength. A constant 8,000-foot pressure altitude and an 80-degree temperature are provided, with an auxiliary pressure system to automatically protect the crew in case of emergency. There are 4 crew members: pilot, co-pilot, bombardier navigator, and defense systems operator. The electronics bay is part of the pressurized area and can be entered by the crew during flight for onboard maintenance. A modular plug-in type of packaging is used and quick-release filing cabinet type of access is provided. Encapsulated seats for each crew member afford protection for escape and survival. The seat may be used at any speed and altitude combination within the flight envelope and down to 90 knots on the runway. The design mission includes a single pre-strike aerial refueling with a KC-135 type tanker. The two aircraft take off and fly together. After flying 1,000 nautical miles out toward the target, refueling takes place. The tanker then returns to base. Range increase on this type of refueling is on the order of 1,500 nautical miles. The primary navigation system employs a stellar-monitored inertial platform. This is an extremely accurate, non-radiating system which is monitored by the bombardier navigator. The system can be started after takeoff and be in full automatic operation after 1 hour of flight. An advanced Doppler radar designed for the B-70 speeds and altitudes and the search radar are activated only for occasional checks and refinements of position information. Unique design features include a side-looking mode which allows a resolution improvement of 40 times for better checkpoint identification. As the SAC bomber penetrates to its target, enemy defense systems must be countered. The B-70 is equipped with an integrated automatic defense system. Intelligence control is centered in a computer which accepts pre-flight instructions and which assesses the enemy's threats by means of radar and infrared surveillance devices. The computer automatically selects the appropriate countermeasures, including ECM, chaff, infrared rockets, and decoys. The defense systems operator monitors the system and may override it if he desires. The weapon bays are housed in the underbody of the aft fuselage and have internal retracting roll-up doors. The forward weapon bay is designed for the Class B weapon, while the aft bay can carry either a Class A weapon or a large bomb bay fuel tank. Weapons are loaded and positively ejected by a translating platform. The primary bombing mode uses the radar to obtain a final fix on a checkpoint several hundred miles from the target. The approach to target and bomb release are then controlled by the computer with position information from the inertial platform. Primary bombing is done at Mach 3 from 78,000 feet altitude. The B-70 continues on to a recovery base for a total range of 8,100 nautical miles. With high-energy fuel, the range would be correspondingly increased. Approaching the airfield, the supersonic bomber has good low-speed characteristics. Touchdown after a mission is at 130 knots. Direct forward and side vision is provided for the pilot and co-pilot throughout flight. The B-70 is designed for a 60-minute turnaround time to be consistent with the alert concept of the Strategic Air Command. When SAC squadrons of B-70s become operational, they will provide the Air Force with a capability for global supersonic strikes, a capability which will serve as a powerful deterrent to any potential aggressor.
This is Edwards Air Force Base, California. As the dawn of October 14, 1965 brightens the sky to the east, the XB-70 awaits its most formidable challenge to date, flight at Mach 3. XB-70 number 1 is being readied for its first flight at 2,000 miles an hour at an altitude of 70,000 feet. The 6 General Electric YJ-93 engines are fired up, each capable of 30,000 pounds of thrust. Aware of the significance of this mission, the ground crew handles the routine of pre-flight operations with great expectancy. With the ground support equipment disconnected, the XB-70's wheels begin to roll. North American's chief test pilot, Al White, and the XB-70 flight test director, the Air Force's Colonel Joe Cotton, guide the steel and titanium giant toward the takeoff area. At the conclusion of a 260-item checklist, the pilot announces the plane's readiness for takeoff.
5, 4,
after reaching a speed of 200 miles an hour, the 540,000 pounds of aeronautical equipment lifts from the ground. The XB-70 pierces the sky over a 2,000-mile course, crossing Oregon, Idaho, Utah, Nevada, Arizona, and California. And then, at 10:06 a.m., approximately 1 hour after takeoff, the word came that everyone was waiting for. From 13 miles above Nevada and flying at a speed equivalent to that of a rifle bullet, the plane's instruments register Mach 3.
Oh, there's that big magic number, boy. That's a boy. Congratulations to both of you.
October 14th is an appropriate date for this Mach 3 flight, for it was on this date 18 years ago that Air Force pilot Chuck Yeager first broke the sound barrier. Since that time, a steady progression of speed goals has been met and surpassed. The XB-70 is a leap into an advanced phase of aviation development. Everything about the plane is imaginative and new, but the solid proof of its ability is coming through flight testing. The success of any flight test program depends upon an intricate and well-coordinated network of support equipment, facilities, and talents. In this, the XB-70 is no exception. Edwards Air Force Base is perhaps the most naturally suited flight test center in the world today. In addition to the 15,000 feet of man-made runway, the 12-mile Rogers Dry Lake bed is available for emergency landings. At least a dozen other dry lakes surround the base, each of them capable of handling the aircraft from Edwards Air Force Base. To the north is a 2,000-mile flight test range, providing many alternate landing fields for the XB-70s. At Edwards, the Air Force maintains a constant support capability for its group of contractors. An example of this support is represented by their parachute shop. The XB-70 has a unique deceleration parachute assembly consisting of three 28-foot nylon canopies, each supported by 32 suspension lines. The triple cluster of chutes in the XB-70 is a first and was specially designed to help break the heavy weight of the metal giant. North American's logistics support site controls over 2 million procured parts, involving some 25,000 line items in this hangar, ensuring the immediate availability of spare parts, supplies, and equipment. Since the beginning of the XB-70 flight test program, this facility has handled over 130,000 transactions. This averages out to about 322 transactions a day. These are 40 by 17.5 lightweight tires, designed to meet XB-70 specifications by the B.F. Goodrich Company. They are constructed of nylon cord and rubber, laminated to a 36-ply rating. The tires are changed after wear has penetrated the top 4 plies. The silver-colored surface is applied to the tires to reflect heat and to keep flight temperatures lower. To detect possible leaks, Air Force personnel apply full pressure of 500 pounds per square inch to the tire for 24-hour storage. If no leaks appear, the tire pressure is released and 100 pounds per square inch of nitrogen gas is introduced to prevent deterioration during storage. Safety features are included all the way through the XB-70 flight test program. To avoid a wide variety of operating problems, guarding against fluid contamination is essential. Each XB-70 contains 280 hydraulically operated devices, such as actuators, motors, and valves. 250 gallons of Aerodynamic fluid is pumped through the plane's hydraulic systems at a maximum rate of 98 gallons per minute. This circulating fluid can reach a temperature as high as 450 degrees Fahrenheit under certain flight conditions. 17 different types of reusable stainless steel filters play a vital role in maintaining the cleanliness of these systems. Systematic replacement is accomplished on all filter elements after a given number of operating hours. Following disassembly of the used unit, its components are washed in a chemical solvent, then bathed in an ultrasonic cleaner. The cleaning treatment is concluded with the elements being heat-dried in a vacuum oven. Contamination can be manufactured into the system during assembly, brought in by new fluids, or generated during normal operations. These brass shavings are typical of the contamination that could accumulate in a filter if the cleaning process were not performed. To assure maximum efficiency and trouble-free flight operation from the YJ-93 engines, a regular inspection is performed. In the event of an engine malfunction, the engine is removed to pinpoint the trouble and to correct it. Basic requirements for all Air Force engines demand that inspections be performed after 25 hours of flight time. However, since the YJ-93 is a new engine, this requirement is doubled, and inspections are performed after 12.5 hours. After 35 hours, the engines are returned to the manufacturer at the General Electric Company's Edwards facility for a complete teardown inspection and overhaul. The engine then undergoes a full-duration 1-hour test to be certain it meets all Air Force requirements. The XB-70 is an experimental research aircraft involved in collecting a harvest of flight information. During its development and flight program, the plane has added significantly to the nation's knowledge about the materials, engineering techniques, and manufacturing skills required to build supersonic aircraft of the future. New dimensions to this knowledge are being added almost daily. The National Aeronautics and Space Administration is spending $2 million to provide flight instrumentation, which is supplementing the Air Force's $12 million for the XB-70 instrumentation package. A total of 800 instrumentation parameters can be obtained from Ship 1 during flight, and over 1,000 from Ship 2. Some of the specific test areas under investigation in the current flight test program include research in stability and control, panel response. Microphones are installed in both ships to monitor overall internal noise, skin friction drag, base drag, or suction pressures on the aft surfaces of the aircraft, structural temperatures and thermal environments, landing loads and fatigue, gust loads or atmospheric turbulence loads, acoustic loads, research in boundary layer turbulence, and sonic boom research. These important contributions to supersonic research are gathered and evaluated from the large mass of data generated by each flight of the XB-70 air vehicles. The tape recorder is capable of 92 minutes of operation. During flight, it is possible to obtain 110 million bits of digital data for future processing and cataloging. The data is distributed to other contractors and governmental agencies, such as NASA, the Federal Aviation Agency, and the Air Force. The information is used to verify estimated data for future designs of high-speed military systems and supersonic commercial flight vehicles. Before a typical XB-70 flight plan can be approved, it is essential that many agencies contribute a wealth of information, knowledge, and experience to the project. For example, the weather commander at Edwards Base Operations receives a continual flow of information from 17 different areas along the proposed XB-70 flight route. The information is teletyped to Edwards with readings of the present weather conditions at various sites. Cloud cover formations, air turbulence at different altitudes, and visibility conditions are of the greatest concern to the pilots. The information is relayed to the pilots at a pre-flight briefing.
Starting out from Edwards on the western leg of the flight will be scattered and broken. The base is around 30,000, topped around 35,000. Going into the Boise area, we're scattered. Winds like variable around to Cedar City, still scattered and broken. Down into the Edwards area, scattered and broken. Bases at 25, tops at 30. The winds at altitude will be light and variable. Temperature at altitude will be a minus 59 degrees centigrade. You should have just a little bit of turbulence in the Hatchby, China Lake area. And any questions?
Here, every phase of the proposed plan is discussed, assuring full coordination of all the flight activities. Still another phase of Edwards' support to the XB-70 flight test program is offered by the RAPCON facility. RAPCON is the radar control system at Edwards. It is a part of a network of 5 Federal Aviation Agency stations, providing air traffic control within the XB-70's normal flight test pattern. The other 4 stations are located at Los Angeles, Oakland, Seattle, and Salt Lake City. An average day at RAPCON can provide service for as many as 200 military and civilian flight operations. Its 100-mile area of authority services such areas as China Lake, Palmdale, and George Air Force Base. As a control station, RAPCON is unique in that the major part of the traffic control is in support of training missions or experimental aircraft test flights. By cooperating with its other agencies, RAPCON offers clearances of civilian and military aircraft along the path the XB-70 intends to fly. As the flight plans are finalized, the physical preparations begin, and the XB-70 is readied for fueling. For this, the Air Force supplies this R1 10,000-gallon tanker. It is the largest vehicle of its type in the world. In the bulk storage area, the tanker is filled with JP6 turbine fuel for transporting to the aircraft. The JP6 is a kerosene-type fuel with a relatively high volatility and good thermal stability. High-performance, high-speed flight vehicles of the future are expected to use fuels with this increased thermal stability. To provide safety during high-speed flights, the fuel tanks are inerted with nitrogen before the fueling starts, and nitrogen gas is mixed with the JP6 fuel by a de-aeration unit. As the XB-70's tanks are filled to the desired point, the nitrogen gas forms a blanket above the fuel, making the ullage space in tanks inert and assuring protection against auto-ignition of the fuel vapors. While on the ground, the XB-70 is entirely dependent upon the ground support equipment, which pumps light through its systems. Basically, this equipment is divided into 2 categories, electrical and mechanical. Typical of the electrical equipment is this MD4 power unit, which provides the same type power that is generated by the aircraft when it is operating. This enables the plane's subsystems to function on the ground without starting up the engines. North American maintains a complete electrical checkout capability at Edwards. A shielded screen room of copper and lead construction keeps out all outside radio interference. Here, checkout is performed on the plane's communications equipment. Other devices are designed to confirm the accuracy of the plane's subsystems. The brake control unit, air inlet control system, auxiliary gyro platform, data control, navigational system, and various panel instruments are all calibrated in this facility. It is essential that all of the plane's measuring instrumentation perform within specification requirements. The hydraulic ground power unit supplies pressure to the various equipment items throughout the plane, offering assurance the units are operating properly. This unit also provides hydraulic power to start the engines. Air conditioning units are designed to provide cooling for crew and equipment in the forward compartment while the plane is on the ground. Coordinating the various ground support units, a mobile communications command post controls the servicing and ground operations. Currently, there is a list of some 1,250 ground support line items that assist the XB-70 flight test program. For all XB-70 missions, the Air Force provides chase aircraft to perform a variety of supporting jobs. On the day prior to flight, a T-38 takes off to cover the proposed flight range. Its objective is to scout the dry lakes and emergency landing fields, being certain they are fit for emergency use. Hours prior to flight, Air Force personnel load rescue equipment aboard a C-130 aircraft. This equipment is ready for use by jumpers and aeromedical personnel who are airborne during each flight of the XB-70. The C-130 then takes off for the high range, prepared to offer rescue service in the event of an emergency landing or pilot ejection.
Start engine number 2, stand by to start engine number 2. Roger, number 2.
As the checkout of the XB-70 is performed, other aerial support aircraft prepare for the flight. For short-range rescue support, the Air Force provides a helicopter to cover the XB-70's takeoffs and landings.
Negative. Data control, the hydraulics disconnected yet? Negative. Utility is disconnected, primary not yet. Roger. Momentarily.
Supplementing the normal helicopter personnel, the crew includes a photographer to document the event, a seat capsule expert, and a flight surgeon, all fully equipped to perform emergency service.
We have all GSE removed at this point, and the airplane is just about ready for taxi. Roger, thank you.
Immediately prior to flight, experienced observers board an F-104 and prepare to accompany the flight for as long as they are able to keep up with the XB-70. Their objective is to offer assurance to the pilots that the mechanical operations of the plane have functioned properly, such operations as the landing gear retracting and the wingtip lowering. From a T-38, a motion picture cameraman provides air-to-air photographic coverage. This film coverage is a normal Air Force requirement for all flights of experimental aircraft. During flight, this control room is the nerve center of the whole operation. Magnetic tapes of all conversations, commands, and responses are recorded for future studies. This is XB-70 ship number 2. In July, the second ship flew for the first time and has now, in 16 flights, progressed to speeds in excess of Mach 2.9.
We'd like him to flutter folks. Let us know when he's going to do it too, please. All right, Jim. Is that any time during taxi? It can be any time. Just let us know. All right. Edwards, data control, Bubblegum. Go ahead, Frank. Ready for flutter pulse now. Roger. Stand by. Doing them now. Now, control cycle, please. It's 30 seconds now, coming up on power. 33 release now.
Engineers familiar with each of the major subsystems watch the development of the flight plan. Constant surveillance is maintained on the air inlet control system, the propulsion units, the chase planes, and the range control. The chase planes act as pacers and offer a calibrated miles per hour speed count. This is a double check on the XB-70's instrumentation. A steady flow of data is telemetered from various sensor points throughout the plane and registered on dynograph recorders. Thermal devices measure temperatures on the plane's skin and engines. Hydraulic pressures, engine vibration, and strain gauge data are also recorded. The real-time benefits of this data permit the flight support engineers to monitor and analyze the most critical parameters throughout the flight, which puts them in a position to advise the crew in the event of an emergency. Thus, the story of the flight unfolds, with the collection of telemetered graphic as well as digital and analog magnetic tape information to form a complete chronological record.
Okay, I got just under 70,000, 292, 532 on the temp, 500 exactly on the airspeed.
During the past 6 months of this report period, the two XB-70 airplanes have flown a series of 31 missions for over 61 hours of flying time. Of this, more than 12 hours was above Mach 2. The two XB-70s are virtually flying laboratories. Every flight represents a tribute to the many people whose coordinated efforts are producing benefits in the form of supersonic research information, applicable to all large, high-speed aircraft of the future.
The horizons of warfare have shifted. No longer are we bound by the propeller-driven skirmishes of the last great conflict. Today, the security of the free world depends upon seizing the high ground, not merely the hills of a battlefield, but the very edge of the atmosphere itself. We are witnessing a bold leap into the supersonic age, a venture spearheaded by North American Aviation to create a machine that defies the conventional laws of drag and heat. This is the XB-70 Valkyrie. It is a weapon forged for a singular purpose: to penetrate the deepest defenses of the Soviet bloc at 3 times the speed of sound. To achieve this, engineers had to discard the aluminum skin that clad our Mustangs and Sabres. At Mach 3, air friction generates temperatures that would melt a standard airframe. Thus, this Leviathan is constructed from a honeycomb of brazed stainless steel, a material so stubborn to work with that entirely new welding techniques had to be invented on the factory floor. Observe the geometry of the wings. They are not static. In flight, the outer sections fold downward, not for storage, but for stability. By drooping these wingtips, the aircraft captures the supersonic shockwave generated by its own nose, riding